In this video, we will look at the external pin interrupts. They can be grouped into either the individual or pin change interrupts, and we look at both the registers and programming examples for both types of interrupts. And remember, if you find this video useful, please like and subscribe. The ATmega2560 has 32 external interrupt pins, which means that the microcontroller can react to a change on an input pin without having to poll it. These interrupt pins are organized into two different types. The first one is the individual external interrupts, interrupt 7 to 0. So there are 8 pins that have their own interrupt vector inside the interrupt vector table. So that's shown here. So we have interrupt 0 to interrupt 7. They have their own vector, and these interrupts are triggered on one of 4 states: a low level, rising, falling edge, or any logical change. Then there are 24 pin change interrupts, PC interrupts 23 to 0. They're grouped into 3 banks: bank 0, bank 1, and bank 2. Now, each bank has only one interrupt vector that's shown here. So these pin change interrupt 0, pin change interrupt 1, pin change interrupt 2. And by only having one vector per bank, that means any pin in the bank will trigger the interrupt service routine, which means after an interrupt's been actioned, the interrupt service routine must poll the pin to see which one caused the interrupt. And the interrupts can only be triggered on a logical change, either a rising or falling edge. So looking at the registers that are used to configure the individual external interrupts, the first one we look at here is the control register A and B. So this determines what condition on the external pin will trigger an interrupt. The bits are grouped into pairs, with each pair configuring one interrupt pin. So the trigger options we have are low level. If the input is low, we repeatedly trigger an interrupt. If we get any change on the input, rising or falling, we'll trigger an interrupt, or a simply falling or rising edge. So we can see the table here and how we select it, and that relates to the interrupt 0, 1, up until interrupt 7. The other 2 registers used for the individual interrupt pins are the interrupt mask register and the interrupt flag register. So the interrupt mask register enables the local interrupt for each pin. So we have INT0 to INT7. When the bit is set and global interrupts enabled, then that external pin is enabled for interrupts. And then we have the interrupt flag register. Now, this is the flag that you can use for polling. So the flag for each of the interrupt sources will be set when an interrupt condition occurs, even if the interrupt itself is disabled. So we can be using that register for polling each pin on the interrupt, and the flag is cleared by writing a 1 to the corresponding bit in the register. So now looking at a coding example for the individual interrupt pins, we have our interrupt 5 is connected to the rotary encoder shown here on the MegaPro board. So when we move the encoder, we want to cause an interrupt, and that will increment an account and output it to port C. So here's the code here. We are including the interrupt library. We have our main loop with no code in the main loop. Everything now interrupt driven. We've got the setups for the interrupts, external interrupts, and our interrupt service routine is shown here. So we're basically incrementing a count and outputting it to port C. And I'm doing this to convert the binary number into decimal for the hex display. So looking at how we configure the registers for these external pins, we're setting the DDRC for an output. The interrupts are coming on interrupt 5, and we want a rising edge trigger. So if we look at the interrupt control registers A and B, and we look at ICRB, we can see that the configuration for interrupt 5 is bit 3 and bit 2. We want it to be rising edge, so we can see that's set to 1-1 for rising edge. Enabling the local interrupts, we come down to the IMSK register, pin 5, so we are enabling the global interrupts, and then finally we are enabling the global interrupts. I have put the code into Microchip Studio, and we can download it to the board, and then we can have a look at it running. So the rotary encoder is on here, and if I turn it, we can see that the count is incrementing every time the rotary encoder is turned. And of course the interesting thing is to note there is no code in the while one loop. Everything is being driven by interrupts. Looking at another example of using the external pin interrupts, we are going to write some code that will sound a beeper when a motion sensor is active. So the active is high, and then we will turn the beeper on when it goes to active, turn it off when the beeper goes inactive. So the PIR sensor is on interrupt 7, and the beeper is on port D bit 5. So looking at subroutines and interrupt service routines, subroutine will be called by software. We can see it here, set it up as a subroutine called in the main loop. The interrupt service routine is called by hardware, so there is no call in the software. We will come into this interrupt service routine when the event causes a interrupt on the pin. Looking at what we are doing in here, when we come into an interrupt, say it was a falling edge, then we turn the buzzer off and we set it for a rising edge for the next interrupt. We have the next interrupt, it's a rising edge, we turn the buzzer on, so then we set it for a falling edge on the next interrupt. And this is how I am writing the code to turn the buzzer on and off when the PIR sensor is active or inactive. Looking at the register settings for the interrupts, we are enabling interrupt 7, shown here in the EIMSK register, and we are enabling global interrupts. And then we can see in here we are triggering the interrupt 7 for either rising edge 1-1 or here falling edge 1-0. I have written the code into Microchip Studio, and I can download it to the Mega Pro board, and we can see it running in action. So the PIR sensor is at the top there. We can see it's been turned on, buzz is going. When it's turned off, the buzzer goes off. So any motion will set the interrupts on and off. And once again, we can see that there is no code in the while one loop. Everything is driven by interrupts. The second group of external interrupts are the pin change interrupts. So the ATmega2560 has 24 of these pin change interrupts from 23 to 0. Now these interrupts will be triggered when the inputs change state, i.e. changing from a high to a low or a low to a high. They are grouped into 3 groups or banks with 8 interrupt pins per group. So we have bank 0, bank 1 and bank 2. Now the interrupt vector table has only one vector for each bank. So we have PCINT 0, 1 and 2 shown here. And because there is only one vector for each bank, your program needs to work out which pin within that bank caused the interrupt. And we can do that shown here. We look at the current pins. Now I'm doing bit masking here. The interrupts are on pin B and I'm ignoring bits 3 and 4. And then I am exclusive ORing the two states. So therefore change pins. Well, the result of exclusive OR is if there is a change, the result would be a 1. If there's no change, the result would be a 0. And so you can use that change pins to work out what individual pins within that bank cause the interrupt. So looking at how we can enable the interrupts on the pin change interrupt system, there are 3 interrupts that we need to enable. We need to enable the individual pins within the bank itself, and finally the global interrupts. So the first register we look at is the pin change mask register, there for bank 0, 1 and 2. So each register relates to a bank. So we have bank 0, bank 1 and bank 2. And then within that register, each bit relates to a pin within the bank. It's PC interrupt 7 to PC interrupt 0, 15 to 8, 23 to 16. So this enables the individual pins within the bank. And finally, we have the bank enable register, so pin change interrupt control register PCICR. So therefore, this enables the bank, for instance, with bit 0, when it is set, then we enable bank 0. And any enabled pin within that bank will cause an interrupt. Note, global interrupts need to be enabled for the system to work. Looking at a coding example of the pin change interrupts, we have 2 LEDs and 2 buttons, and we want to toggle the LED when a button is pushed, but we want to use the pin change interrupts rather than polling. So the buttons are on PC interrupt 0 and PC interrupt 1, and that's on the bank 0, the interrupts. The 2 LEDs are on port C, bit 0 and port C bit 1. So looking at this more detail, the buttons are on bank 0. When a button change occurs, then the interrupt vector will be actioned. We need to determine what button caused the interrupt. Note, the interrupt occurs on both falling and rising edges. If it's on a falling edge, we want to take no action. Now I am going to use a simple delay in this function, but you shouldn't use it in practice. You should really set a flag and do your debouncing in the main looper timer. So here's the structure diagram. We have start, set up, while 1. There's nothing in our while 1 loop, as we can see here. We're setting up the registers. Let's scroll this down a bit so we can see. Setting up the registers. Now, the setup is called in the main function, but the interrupts are not called anywhere by software, they're called by hardware. If I look at the pin change interrupts, then I determine which pin caused the interrupt. If button 0 caused the interrupt, and if that button's high, toggle the LED, delay 10 milliseconds. If button 1 caused the interrupt, and it's high, toggle the LED, delay 10 milliseconds. That's LED 0 and LED 1. So looking at the code, we can see the pin change interrupts shown here. Once again, we look at the current pins, and we've got the bit mask shown here, because we're only looking at bit 0 and bit 1. We are excluding all the previous pins with the current pins, and then we'll use the change pins to determine if it was interrupt 0 or interrupt 1 that caused the interrupt. If the button is high, then we will toggle the LEDs and then delay. And finally, looking at the setup routines here, we're setting up the port C, the LEDs for output on bits 1 and 0. We're initializing the mask, looking at pin B, which is the bank 0 input. We are enabling the bank, so this is the PCICR, we're setting that bit to a 1 to enable bank 0, and the interrupts PC interrupt 1 and PC interrupt 0 are being enabled in the PCNSK 0 register. That's how we're configuring the interrupts. And of course we are enabling the global interrupt.